talk about equiangular lines with fixed angle.
Thanks to Shira for the invitation. Hello, everybody. My name is Zilin, and from MIT. And if anyone is watching on YouTube, hello as well. Okay, so the protagonist today of this talk is called equiangular lines. So it's a set of lines in RD, pairwise separated by the same angle. So it's a very symmetric configuration of lines. By the way, all lines are through the origin. So here are several examples. In 2D, we can place 3 lines through the origins, pairwise separated by 60 degrees. And you could think about it. You could not fit more than 3 lines so that pairwise separated by the same angle. If you were to place 4 lines, then the adjacent ones should be separated by 45 degrees, but there are 2 orthogonal which are not separated by the same angle. Is this clear? Okay. And in 3D, if you think about it, you can say consider a point to the vertices of the simplex. You can place a tetrahedron, but you can do better than that. Actually, if you take icosahedron, and consider the 6 diagonals, main diagonals of icosahedron, then you will also get a set of equiangular lines. And it turns out that in 3D, this is the best you can do. You can place at most 6 lines. Okay. Equivalently, we can represent the configuration of equiangular lines by unit vectors. For each line, I can choose a direction of the line, and that corresponds to a set of unit vectors. I'll change the color. And if these unit vectors come from equiangular lines, then you know immediately the pairwise inner product of these unit vectors will have the same absolute value. Okay? The reason for absolute value is that if an angle is the angle I prescribe, say 60 degrees, the inner product will be cosine of 60 degrees or cosine of 180 minus 60 degrees, which is minus cosine 60. Okay? So unit vector pairwise inner product equals plus minus a number. So for that number, I will use plus minus alpha. Okay, so that's the parameter. And the angle here, if I really want it, then is arc cosine of alpha. Okay. And for this set of unit vectors, usually they are called plus minus spherical code, and for this talk, I will just call them plus minus code, alpha code. And as you can see, sort of these 2 models are roughly the same concept, except the following. So for example, for the 3 lines on the plane, I can choose 3 unit vectors like this, but also I can choose the opposite of a unit vector, and they still correspond to the same set of lines. Okay, so basically these 2 concepts are the same up to something called switching. By switching, I basically mean for a unit vector, you can choose the opposite of it. Okay. So historically, the following problem has been concerned. So find something called MsubF of D, which is the maximal size of a plus minus alpha code in RD. Okay. So that's my, this is the main function I want to study. In other words, how many lines can I place in D-dimensional space so that the pairwise angle is fixed and they are the same, i.e. arc cosine of alpha. Okay? Or there is another function I can try to study, which is that I choose the optimal alpha angle and I try to maximize it. In other words, now I don't restrict the angle between the lines, and I want to find the maximum number of lines I can place, equiangular lines I can place in RD. Okay, so what do we know about these functions? Okay. So you can look up the online Encyclopedia of Integer Sequence, A002853. It tells you that this n of d is equal to 1. That corresponds to dimension 1. You can only, it's not so interesting. And the 2 dimension, you get the optimal 3 lines, 6, 6, 10, 16, 28, 28, 28, 28, 28. Of course, you would guess that it continues like this forever. But what we know is that n of d is upper bounded by d plus 1 choose 2. Okay, that's the some upper bound you can get. It has a very nice linear algebraic proof that was done by Girton in 1973. And people didn't know that whether n of d behaves like quadratically or linearly. But to 2000, the Kane made a beautiful construction that shows it grows quadratically. Okay? So you know it doesn't continue as 28, 28 forever. Okay. And I just want to point out several interesting numbers here. So we had this upper bound d plus 1 choose 2, and we reached that upper bound when in 2 dimension, in 3 dimension, and in dimension 7. Okay, so you have already seen the 2 construction for dimension 2 and 3. And for 7 dimension, let me just say some fancy words. The construction corresponds to the weight vectors of 56 dimension representation of E7 of some Lie group. Okay. So since the topic today is fixed angle, so I will not focus on this. But if you're interested, here are some open problems regarding n of d. So can you find this for some d bigger than 23? Okay. So actually that means when d is equal to 23, this bound is also achieved. Okay. But for d larger than 23, we don't know whether we can achieve this bound again. Okay. And another question is n of 14, whether it's equal to 28 or 29. We also know that. Don't know that. Okay. So as I said, I will the rest of talk will focus on this function MsubF of D. Okay, the angle alpha is fixed now. What do we know about that? Lemons and Seidel showed in 73 that if this alpha is 1 over 3, okay, this inner product will be plus minus 1 over 3. Then this is equal to 2 times d minus 1 when d is at least 15. Okay. And Newman in 89 showed that when alpha is 1 over 5, this is equal to 3 over 2 times d minus 1 when d is large. Okay. Something like d is larger than 50,000. Okay. You may ask, why do people care about 1 over odd number? Because if you think about it geometrically, that means the angle is arc cosine 1 over 3 or arc cosine 1 over 5. They are not nice angles like 60 degrees. The reason is that Newman showed in 73 that this number is at most 2d unless alpha is equal to 1 over 2k minus 1 for some positive integer k. Okay? So if you really care about the problem for n of d, to maximize n of d, one should look for alpha of the form 1 over odd number, roughly speaking. Okay? So focus has been on this. And for a while, actually, people don't know if alpha is 1 over an odd number, I will get some linear upper bound on how does the function behave. By looking at these, you would expect that when alpha is fixed, this function is a linear function. So that was actually shown by Boris Buch in 2016, that this is indeed upper bounded linearly. Of course, you can achieve a linear lower bound by just taking the standard basis in d dimension. They form equiangular lines. So basically, it means the function behaves linearly. And this result was, but this C alpha is very, very bad. And in a paper by Bala, Drexler, Sudakov, and Kivash in 2017, they showed that this function is upper bounded by 1.93d plus big O of 1. Here, this big O of 1 will depend on alpha, and in the rest of talk, all big O will depend on alpha, so I will suppress the subscript. Of course, this is wrong because of this result, so you only need to write when alpha is not equal to 1 over 3. Okay? So by looking at these two formulas, Book, in his paper, he conjectured the following. N sub alpha of d is equal to k over k minus 1 times d plus big O of 1 when alpha is 1 over 2k minus 1. Okay? So you can check when k is 2, alpha is 1 over 3. This shows you 2 over 1, matching this one. And if k is 3, then alpha is 1 over 5, and this is 3 over 2. Okay, so that's the natural generalization of these two results. Of course, here we need this O of 1. Okay, so that's all about the, everything before my work and joint work with others. Is there any questions before I continue, please?
In 7 dimension and higher, you have a 28 for n sub d value over there.
Yeah.
As dimension changes, those numbers coming from the same fixed alpha or different alpha values?
From the same configuration. So increasing dimension doesn't actually help.
Okay, so it's fixed
Yeah.
alpha.
Yeah.
Okay.
Oh, you mean?
Yes.
Yes,
all
yes,
those
yes,
points.
yes. Increasing dimension don't change the extreme configuration. Any other questions?
It's just to make sense between that omega of d squared lower bound and these linear upper bounds.
Yeah.
These constants must be pretty terrible, right? Like these
Yes.
go of one kind
Yes.
of. Yeah, okay.
But also here the result is about large D. So that's actually a frequently asked question whenever I give this talk or my collaborators give this talk, because seemingly there is a contradiction between the result. Over there we know n of D behaves quadratically, but here when alpha is fixed it's linear. So let me maybe just explain briefly why there is no contradiction in mathematics. So let me mark here the dimension. There will be 2, 3, 4, etc. And let me, here it represents alpha, but I will not draw them to scale, but rather, it starts from 1 and ends at 0 and not drawn to scale. And I mark the interesting points. So what do we know about from the linear upper bound? If I fix the angle and increase the dimension, the numbers I will see here approaches, for example, on this line approaches 2D. Okay? For 1 over 5, this line, the values on this line approaches 1.5D. Okay? And for the others, according to BDSK result, they are bounded by 1.93D. And on the other hand, if you fix dimension and let alpha go to 0, there is a result that tells you all this goes to D. Okay, the dimension is 2. As alpha decrease, they go to 2, 3, etc. So in order actually to make sense of this quadratic behavior of n of D, the only explanation is that all the interesting maximizers for n of D, the extremal configuration, live in this corridor. Okay? And in particular, here you will see the diagonals of a hexagon and the octahedron, and also E7 somewhere here. Okay. Shall I continue? Okay. Okay. So in the joint work with Alexandr, instead of proving the conjecture of Buch, we didn't manage to do that, but we can generalize the conjecture, because why not? So here's a conjecture that generalizes Buch's conjecture. It will look exactly the same, but it's different. Okay, but here let me explain what I mean by k. K is some function of lambda where this lambda is equal to 1 minus alpha over 2 alpha. Okay, it just turns out that parameterizing the problem by alpha is not as it's not so essential. You can actually parameterize the problem by this lambda, which is just a rational function of alpha. And this is the smallest order of a graph G with the largest adjacency eigenvalue lambda 1 of g being equal to lambda. Okay, so here, whenever I say largest eigenvalue of a graph, I mean you take a look at the adjacency matrix of the graph and compute the eigenvalues. And I will use lambda 1 of g to mean to be the largest eigenvalue. And in general, I will use lambda 1, lambda 2. And if the graph has n vertices, it will have n eigenvalues. Okay? So maybe initially it's very hard to see why it's a generalization of Book's conjecture despite the same form. But maybe let's compute several k for different alphas. Okay? So when alpha is equal to 1 over 3, right, in the Lemons-Seidel result, the lambda we will get is 1 minus 1 over 3, or 2 times 1 over 3. It's equal to 1. Okay? And which graph, what's the smallest graph achieving the largest eigenvalue 1? Well, you can take an edge. An edge will give you that. And an edge has 2 vertices. Okay? And if you take 1 over 5, you compute that, you get 2. And this time, a triangle is the smallest, and it's has 3 vertices. Okay? Actually, how do you see if a triangle is the smallest graph achieving the largest eigenvalue to be 3? There is a theorem that says if H is a subgraph of G, then the largest eigenvalue of H is at most the largest eigenvalue of G. And furthermore, if G is connected, then the inequality is strict, proper. Okay. So once I take a smaller graph of this, I will never achieve the same largest eigenvalue. And here is another interesting parameter. Okay, and if you compute that, you get lambda equals root 2. And that's achieved by a cherry. So again, this is 3. Okay. So now I hope it makes sense to say this conjecture is a generalization of Book's conjecture. And of course, Polyanskii and I proved something. Okay. So we proved that this conjecture just generalize the conjecture holds for all lambda at most 2 plus root 2 plus root 5, which is approximately 2.058. Okay. In particular, we can show that when if alpha is equal to this number, 1 over 1 plus 2 root 2, the function behaves like 1.5 times d plus big O of 1. So, in the joint work with Tidor, Yao, Zhang, and Zhao, we actually resolve this conjecture in the following strong form. So n alpha of d is equal to k over k minus 1 times d minus 1 when k equals k of lambda is less than infinity and d is much larger, which is larger than a constant depending only on d, on alpha. And also when k of lambda is infinity, we can get such result, d plus little of d. Okay. So here we have, sometimes we will have this case because the lambda you get maybe is just say a transcendental number. So no graph will achieve such thing, right? No graph will give you lambda as the largest eigenvalue. So it's also possible. Okay. So for the rest of the talk, I actually want to convince you that these results actually are highly related to a couple of results we discovered in spectral graph theory. And I want to explain why there is such a connection. Okay. So for the result with Polyanskii, actually we studied the following problem in spectral graph theory. So okay. So consider a family of graphs parameterized by lambda, which is a collection of graphs G with lambda 1 of G being at most lambda. So think about your favorite lambda and just collect all the graphs with largest eigenvalue at most lambda. Well, what kind of property do we know about this family of graphs? According to this fact, this family of graphs is closed under taking subgraphs. Okay, if you take a subgraph, it will have possibly smaller eigenvalue. So it's closed under taking subgraphs. So for such family, you can ask the following question. Can we actually describe this family by a finite set of forbidden subgraphs? So if you are not familiar with this kind of family and family of graphs and the characterization, think about how do you describe the family of planar graphs. And you say it's a planar graph, it doesn't contain K3 subdivision or K5 subdivision. Right? So that's a very similar flavor. You want to say if I have a family of graphs closed under taken subgraph, I want to describe it by a finite set of forbidden subgraphs. So the first question we try to answer is when does f of lambda have finite subgraph characterization? Okay. And that's somehow related to the result with Polyanskii. And for the second result, we try to understand the following problem. We want to actually bound the multiplicity of the second of, let me just say, lambda 2 of G. Given a graph G, can we actually bound the multiplicity of second largest eigenvalue? And by answering those two questions enabled us to prove results about Equiangular lines. Any question before I move on? Okay. So how did we arrive at these two questions? Again, we want to study plus minus alpha code in RD. Okay. And we know it's a set of unit vectors. Okay. I want to study a corresponding graph to this code. Okay. Well, it just turns out that the vertex set is also V. So I just take the set of vectors and use them as my vertices in the graph. I know the inner product is equal to plus minus alpha. So to encode that information, I say here I put an edge between two vertices if the inner product is equal to minus alpha, that encode the negative information of the inner products. So somehow, when you see the graph, you should be able to recover the inner product, whether they are positive or negative. What do we also know about vectors in RD? Well, there is something called the gram matrix. Okay, if you've never seen it, don't worry. It's some matrix you can make out of the vectors. And we know that it's always positive PSD, a positive semi-definite. And the corresponding language we will adopt here is that if you compute m over 2 alpha, you will notice that it's equal to lambda I, which the lambda is defined before. It's 1 minus alpha over 2 alpha, minus the adjacency matrix of A, plus half of J. J is the all-one matrix, being PSD. Okay? Adjacency matrix, all-one matrix. So that's the direct translation of that. And now we also know that the rank of this gram matrix is at most D, since this gram matrix comes from vectors in D-dimensional Euclidean space. So the rank of that is D. So here, in general, we want to, so here the goal is actually to try to maximize the cardinality of V. Right? I want to put as many vectors in RD as possible to maintain the inner products. But just for the purpose of this talk, I actually want you to think about the other way. So here is like given D, given the dimension, I want to maximize the size of the vectors. But rather, I want you to think about this way. So say given the size of vectors, I want to minimize the dimension of D. It just turns out that it's easier to think about it this way and don't lose the essence of the argument. So here, what we do is the following. Given a graph, and I know the size of the vertices, and I want to minimize D. What's D here? That's the rank of this matrix. Right? So we want to minimize the rank of lambda I minus A plus half of J. Okay? Know that J is a rank 1 matrix, it's all 1 matrix, so the rank is 1. So basically the rank of this, if you allow me to cheat a little bit, is the rank of lambda I minus A. So to minimize the rank of lambda I minus A is actually the same as maximizing the multiplicity of lambda as an eigenvalue of the graph G. Sort of here you get high multiplicity, here the rank will be smaller. So that's somehow you already see multiplicity popping up here. Okay. So I will mark this condition as PSD. So let's look at some consequence of this PSD condition. If I know a graph G that satisfies the PSD condition, what can we say about the graph? So the PSD condition, if I rearrange it, it tells me A is dominated by lambda I plus half of J. Okay. There is something called some type of memax theorem that says the second largest eigenvalue of A is bounded by the second largest eigenvalue of the other side. And what's nice about this second largest eigenvalue of this matrix is that the second largest eigenvalue of J is equal to 0. Although the the largest eigenvalue of J is the size of the matrix, the second largest drops drastically to 0. So this is equal to lambda. Okay. So it's already really powerful. It tells you that the second largest eigenvalue of a graph is at most lambda. Now I want you to think about the kinetic component decomposition of G. So suppose G has n components. And what we know about the spectrum of G is equal to the spectrum of G1, Gi, take the union. This is equality when we consider the spectrum to be a multiset. Okay. So since G, the largest, second largest eigenvalue of G is at most lambda, well, what can we say? You see that at the end of the day, we want to maximize the multiplicity of lambda as an eigenvalue of G. Okay. So somehow lambda has to appear, if I can, as many times as I want, I can in the spectrum of Gi. So it just turns out that there are two cases we need to consider. Okay? In the one case, I will call it a completely reducible case. Which says the largest eigenvalue of each connected component is equal to lambda. Okay. And there is an irreducible case, which says the lambda 2 of G is equal to lambda, and there is only one connected component. Okay. These are the only interesting cases we need to consider. For example, one can say maybe all the largest eigenvalue of Gi is less than lambda, but that's not interesting because at the end of the day, we want to maximize the multiplicity. So whenever I see a connected component having largest eigenvalue less than lambda, I actually should not use that connected component. It's a waste of the vertices I have in my hand to spend. Right? And you can also rule out the case where one of the connected component has lambda 2 to be lambda, and the rest have largest eigenvalue to be lambda. That's also something you can rule out by application of memax theorem. Okay. So let's first look at the completely reducible case. Suppose I know the largest eigenvalue of each component is equal to lambda. What can I conclude about the multiplicity of lambda? There is something called the Frobenius theorem. That says if you have a connected graph, then the largest eigenvalue is simple, has multiplicity 1. So each connected component can contribute at most 1 to the multiplicity I want to maximize. Right? So what kind of graph should you choose for each component to actually maximize the number of components? Right? At the end of the day, I will get the number of components as a multiplicity. Let me just write here. Multiplicity of lambda as the eigenvalue of G is equal to the number of components. Well, I should choose G to be the smallest graph, which is the largest eigenvalue. Okay? And that roughly says M will be bounded by the number of vertices divided by K of lambda. Right? Each component will now occupy K of lambda vertices. Okay? And hence, if you play with around, you will get the formula I talk about in the conjecture. Okay? So somehow here the idea is actually to understand the irreducible case. Okay? So idea number 1. Well, irreducible case never occurs? Question mark? Okay. Maybe we haven't used the PSD condition enough, right? We just take the second largest, we just did some memax theorem here. Maybe the PSD condition will tell you the irreducible case never occurs. Hence, we are in the completely reducible case, hence the conjecture. Okay? So that's actually the starting point of the project with Polyanskii. We try to understand the limit of this idea, basically.
Why is it enough to consider why in the irreducible case m equals 1? Why can
Yeah, m could, yeah, so one can use some memax theorem to rule out the possibility that m is larger than 1. Yeah, with still the, yeah. I didn't say, but one can rule out that. Yeah. Okay, so here's a fact that's used repeatedly. So for every set of graphs, a finite set of graphs with lambda 1, the largest eigenvalue of each one bigger than lambda, okay? If G satisfies, a graph satisfies the PSD condition. Okay, here I omit some words, but I will come back to that. Then G does not contain any of the graph I listed as a subgraph. Okay, so here there are some small prints to this statement. G satisfies PSD, and G, large enough. It's a large graph, and I need to do some switching. Okay. So there is still a notion of switching in graphs, as we can do switching for vectors. You can also, they carry the same notion to graphs, and also and up to discarding some constant number of vertices. Okay, but we don't care about details. Basically, the fact is quite powerful. It says that whenever you write down a finite set, what I will call forbidden subgraphs, f1 through fk, with largest eigenvalue bigger than lambda, then if G satisfies PSD, the PSD condition will tell you G does not contain f1 through fk. Okay. So why is this fact helpful and connects to this problem I studied with Polyanskii? Well, the theorem with Polyanskii this f of lambda, the family of graphs, is equal to graphs with no there exists f1 through fk with lambda 1 of fi bigger than lambda, such that f of lambda is equal to graphs with no f1 through fk, meaning that f of lambda, the family we considered, has a finite subgraph, forbidden subgraph characterization. If and only if lambda is less than this magical number, and lambda is not equal to some exceptional, countably exceptional numbers I can make explicit of that, but let me omit the detail between 2 and this. Okay. So it's if and only if result. So you can only do this finite forbidden characterization for such lambda. Okay. So a corollary of the theorem, with together with the fact, says the following. So imagine I have a graph that satisfies PSD. Okay. I take a finite forbidden subgraph characterization for my f of lambda. Okay. I plug in, use those f1 through fk, plug in this fact here. It tells me that G does not contain any of these, right? So if G satisfies PSD, then G does not contain any of F1 through Fk, meaning G is inside the family. But recall the definition of this family just tells me this is at most lambda 1. Or lambda. The largest eigenvalue of G is at most lambda. So for these lambdas, I know the irreducible case never occurs. Hence, we can solve the conjecture for lambda at most √2 plus √5. Okay, although you need to handle some corner cases where lambda is equal to this number and the lambda is equal to those. Oh, we can do that. Okay, so this idea basically is that, because I feel like we pushed it as hard as we can. So the second idea that initiates the paper with colleagues at MIT is the following. The irreducible case underperforms the completely irreducible case. Okay, underperforms, I mean the following. Can we actually have some result of this form? The multiplicity of the second largest eigenvalue of a connected graph is little of n. Right? Recall that in the completely reducible case, the multiplicity we get is linear. It's n over, n is the number of vertices, n over k of lambda. Right? And if we have such result, then that means in the irreducible case, the multiplicity will be sublinear. So it underperforms the completely reducible case. And for that, we show the following. So for every connected graph G with degree bounded by some constant delta, the multiplicity of the second largest eigenvalue is equal to big O, some constant depending on delta, n over log n. Okay? In particular, it's sublinear. So why does this imply irreducible case underperform CR? Here you notice that I have this extra condition to have bounded degree. And actually it follows from the fact. From the fact, I can choose a star, a very large star, with about, say, lambda square plus 1 leaves. And the lambda 1 of that, of this star, is bigger than lambda. Okay? So by the fact, you can say, I can forbid this big star in my graph. Then forbidding star is the same as having maximal degree less than lambda square plus 1. Hence, for those G satisfying the PSD condition, we can apply the theorem and get a sublinear upper bound on the multiplicity. Okay.
And this is best possible?
That's a good question. So here is an open problem. Actually, can you is it actually true that this is big O of n to some epsilon that you can specify? Is this true? Can you find a positive epsilon such that this is n to the 1 minus epsilon? We know a lower bound of this. It comes from calligraph of some calligraph. Let me just say it this way. And they use representation theory. You can show that this can be as large as cubic root of n. So you cannot put any number larger than 2 over 3 here. That's all of my talk. Thank you for attention.
So going back to book conjecture, does this settle it, or is there?
Yeah, we almost settled it, except that we don't know, like, precisely if k of lambda is equal to infinity, meaning the lambda is not transcendental, but there are some other cases where lambda is algebraic number, but k of lambda is infinity. That's also open. Can we show this is equal to d plus some constant error, where currently what we have is little of d. So that's also, but for the case where k of lambda is finite, I think we completely solved the problem.
Another question? What else is known about these properties f of lambda? So, like, is there a finite, let's say, basis of them that the disjoint union of them generates this property or anything like that?
By property, you mean generates this family?
Yeah.
Disjoint union? Disjoint union of what?
Oh, what I'm asking is, does there exist a finite set of graphs for which every graph inside that family is a disjoint union of those graphs?
Oh, actually, so let me just talk about examples. So consider the case where lambda is equal to 2. Actually, in this family, again,
cycles, okay.
Yeah, cycles and path. Path is also, yeah, so it's not like that. But you can describe this family by forbidding finitely many graphs. And somehow, if you've learned some representation theory, there is something called the Dinkin diagram. And basically that corresponds to classification of graphs in f of 2. Yeah. And sort of here we see the reason why we can do such classification.
Okay, let's go again.